All right, welcome back to video 2 of week 7 of Physics 325. Today we're going to talk about lenses. Now lenses technically are part of optical instrumentation, and as such they belong in the third part of the course. But they're such an integral part of like lab and tabletop and everyday diffraction experiments that we really need to talk about them now. So we're going to do a sneak preview of lenses this lecture and talk about how they relate to diffraction. So just as a recap, what were we discussing last time? We were talking about the problem of diffraction. And that is, given the field at say z equals 0 along the x prime y prime plane, what is the field downstream? In other words, some distance z away. We applied the paraxial approximation and we said, well, whatever that field is, we can think of it as a bunch of spherical paraxial wavelets that are coming down the z-axis or near the z-axis and forming this pattern at some other distance z. And just writing this down in equation form, we came up with this Fresnel diffraction integral. This is really just in equations what I just said in words. We're just integrating that whole aperture over every possible wavelet. Now, if we look at this equation, we could also call it the almost Fourier transform of f of x prime y prime. Okay, so it's very nearly the Fourier transform, but it's not quite the Fourier transform because it has this quadratic phase factor in this curvature term, rho squared. And if we can get rid of that, we have the exact Fourier transform at a distance z. Now, we found out one way to get there. We can go into the so-called far field. When we're sufficiently far away from the source, that rho squared over z is much smaller than the terms making up the Fourier transform, and we can just get rid of it. And we have this integral, which is indeed the Fourier transform. It's the actual Fourier transform. It turns out that's for very small, like few tens of microns apertures and optical wavelengths. That's on the order of a few meters usually to really be in the far field. And if we're even smaller, we can, like a 1 micron pinhole or something like that, we can be in the far field a bit closer. But even for millimeter objects, we still have to go fairly far away, and that's not always convenient. So we're going to talk about a way to map ourselves into the far field. I have one here. This is a lens. This lens is going to be our far field converter. So when I'm shining light onto it and looking on the screen, at focus, it turns out I'm going to see a distribution which is exactly what I get in the far field. This is either a lens, as we'll talk about it in a little while, or it's a Fourier transformer. And how it's going to work is it's going to get us to the Fourier transform by getting rid of that problematic rho squared term. If we can get rid of that rho squared, we're golden, and we have the actual Fourier transform. So let's dig into what a lens is. Now let's look at the geometry of a lens. Typically we have, if you imagine a spherical surface and we slice some of it off, we have a portion of that sphere. That is what our lens is going to be made out of. And if we have a flat side here, if we have one of the sides just chopped off, that is what we call a plano-convex side. One of the sides is a plane. All right. So just a reminder, what is the equation of a sphere? Well, at the origin, it's x squared plus y squared plus z squared is equal to the radius squared. And we can offset in x, that'd be x minus x naught, y minus y naught, etc. So this is the equation of a sphere at x naught, y naught, z naught. And it's just given in this form. Okay, so we're going to work as usual in the paraxial approximation. So we'll let the distance be along z, and we're going to effectively make this a two-dimensional problem. So let's just say that x is equal to 0 for now. Y will be up and z will be this way. Okay, and we can therefore write an equation of how far we need to move along the z-axis before we hit the lens. So our equation in this case for z equals 0 looks like y minus y naught. So that's y squared plus z minus r squared is equal to r squared. That's our equation for our sphere. And therefore, z minus r is equal to plus or minus the square root, if we get this y over to the other side, r squared minus y squared, right? So z is equal to r plus or minus this, r squared plus y squared. And we can see that it's going to be, if y is small, right, this is going to be give me an answer at near 0 and near twice the radius. And we can see that's the front and the back face. So let's talk about the front face. We'll get the difference here. And we can write it that way, or even 1 minus 1 minus y over r all squared. We've seen this kind of approximation quite a lot in the course, haven't we? Okay, so given this, we're going to work in the paraxial approximation. Let's let that y over r, the displacement up and down, let's look at angles only for which that displacement is small. In other words, this term here is going to be small, so we can use the Taylor expansion, 1 minus, and this is going to be 1 minus r squared over 2r, y squared over 2r squared, and these ones are going to cancel. This will become a plus, so this is going to become z of y is approximately equal to just y squared over 2 times r. All right, so this is the equation for the distance I have to go from the z equals 0 plane to hit the lens. So there is nothing special about y. We could have chosen x as the angle or some angle in between. So imagine we're looking directly down. I chose going up and down this way. That's y. We could have chosen this to be our transverse axis, x. In general, it's just going to be anything here. So we'll call this rho, as usual, kind of our cylindrical coordinates. We'll define that as the square root of x squared plus y squared. So this holds along any angle along the xy plane, and we're going out in z. Okay? So we'll just make that three-dimensional, and we'll write it in terms of rho instead of y. So let's think about the action of this lens, what it's actually doing. To start with, we'll imagine plane waves coming in and hitting this lens here. In fact, that's what we have drawn here. The plane waves are coming and they're going to strike this, this lens. Now the plane waves, if we just look at a wave along the z-axis, right at z equals 0, it hits that glass. But if we move up a bit, the wave has to travel a bit further in order to hit the glass lens. And that means that those rays that are above and below the axis have to travel a bit further in air, which is actually a bit faster because n of glass is 1.5-ish and n of air is 1. It travels at the speed of light, roughly, in air. So let's work out exactly how much it has to change. Okay, so let's look at the effect of a lens in terms of this, in terms of its geometry. And what we're going to do is we're going to look at the field. It's all uniform until it hits that z equals 0 axis. And then it's going to go along to the end of this plano-convex lens. We call that end T. And again, apologies if I'm not pointing at the exact right spot, but you get the idea. We'll solve for the state of the field directly after the lens at the z equals t plane. Okay, so let's look at the state of the field there. So we've gone a distance z in air and a distance t minus z in glass. And remember, we have the formula for z now in our paraxial approximation. It's approximately equal to rho squared over 2r. Okay, so we can actually solve for this. Let's work it out. Let's work out the math. So at a given height z, we've acquired a phase. We have the air part, k times z rho, and this is going to get cumbersome, so let's just call it z for now. And that's in air. And then we have propagation t minus z in our index n. N k t minus z. Okay? And this is in the lens, or glass, or whatever we call it, index n. Okay, so let's just do this. Let's just grind it out. So we're going to get e to the what? To the in. We're going to get z plus n times t minus n times z. That looks about right. And we'll collect all the terms with z. So we're going to get, we'll throw that e to the I n kt out. This is what the beam would be if there were no lens there. And we also have this other stuff involving z to contend with. And that is, well, if we stare at it, we're going to get a 1 minus n. So I'm going to write this as e to the minus I n minus 1 times z, which is rho squared over 2r. Yeah? So this is the state of the field directly after the lens. This is the field in terms of its phases. Here, we haven't lost any intensity, so E naught is whatever it was before. But now we have a field which looks like this. This looks startlingly familiar, right? This is actually the equation of a paraxial wave centered now to the right instead of the left. So we have this minus sign here, some distance away. So remember the paraxial wave equation, the paraxial spherical wave, we had e to the I n k z times e to the I plus I, because it was to the other side, rho squared over 2z. So it's like a spherical wave with a different origin, right? We're to the right instead of to the left, so we have a minus sign. And the origin is what looks like it's at what we call f, which is equal to r over n minus 1. By the way, we're going to call that the focal length. This is what we have for our lens. It takes a plane wave and it turns it into a spherical wave with an origin at what we call the focal length, f, which is r divided by n minus 1. R is the radius of curvature of the lens. Let's look at the effect of a lens. What is it actually doing? It's now we can see another way of thinking about a lens. We're going to think about it as a magnifying glass and an object in a telescope and microscope later, some eyeglasses a bit later. But for now, what it is, it's a converter of plane waves to spherical waves. How does it do that? More fundamentally, what it is it's an imprinter of quadratic phase. It imprints a quadratic phase on whatever is coming into it, this rho squared over 2r. And that has the effect of converting these flat plane waves into a spherical wave, okay? This is all reversible, right? I don't show you which way these arrows go. In fact, optics is completely reversible this way. So if something happens this way, it has to happen this way. This is actually a deep result in optics. So that means I can reverse it. I can take a spherical wave here, send it this way, and convert it into a plane wave. When I take a plane wave to a spherical wave, I call that focusing. When I take a spherical wave and turn it into a plane wave, I call that collimation. Okay? And what did I actually do there? Well, you can think of it this way. I took a spherical wave and I put it a distance away, a very special distance away, because then we have this reversibility argument, and I had a spherical wave in and a plane wave out. But there's no law of physics saying I have to put my light source or whatever I'm imaging a distance r away. What happens if I put it somewhere that is not? So let's work that out now. Let's see what that's going to look like. In general, it's going to look something like this. So let's just take a general spherical wave, some distance, we'll call it dO, because we're going to call it the object, away from the lens, okay? And let's look at the state of the field directly before the lens, okay? It's given by this, e to the I, k, rho squared over 2d object. This is just nothing other than our paraxial spherical wave equation, okay? This is what it is directly before the lens. How about directly after the lens? Well, we know what the lens does now. Anywhere on some height rho above the lens, it's going to impart a quadratic phase shift, rho squared over 2f, okay? Minus rho squared over 2f. So directly after the lens, we have this equation in yellow here. We have our input field with our rho squared over 2d object times our quadratic phase shift, okay? And if we look at that, what is that? I can factor a bunch of stuff out. It's gonna give me e to the I, that's common to everything. K, that's common to everything. There's rho, that's common to everything over 2. And then something with units of 1 over meters. 1 over meters. And we'll call that di, right? I don't know what the number is yet, but it's going to give me something with units of meters, inverse meters. So whatever I get there, rho squared rather, I'm going to get some other spherical wave. So I'm going to map spherical waves to spherical waves. But what is the origin of this new object here? Okay, let's just directly compare. And before I go any further, the suspicious among you might notice that I've pulled a little bit of tomfoolery, if you will. I've actually neglected any propagation that happens through the lens. I kind of instantly teleported from immediately before the lens to immediately after. And indeed, if I actually have a lens which has some non-negligible thickness, I do have to take this into account. But what we're going to do for now is we're going to neglect any extra phase that happens. We're going to talk about this quadratic phase that's imparted, but we're going to assume the light here is just e to the I k rho squared over d times d object, and then instantly warp to the other side where it's that same field times the quadratic phase vector. This is called the thin lens approximation, where we say that effectively all this lens does is impart a quadratic phase, but we don't worry about any extra little delay that occurs during the thickness of this lens, okay? Had to get it off my chest, and that's what we're going to apply here. But having said that, let's just look what we have here. If we just compare these terms, we have the product of two things. We have e to the I k rho squared over 2 times 1 over d object, just collecting terms here, minus from the other term 1 over f. That's equal to some other plane wave, I k rho squared over 2 times 1 over d image. And comparing these two terms here, we have d object minus inverse d object minus inverse focal length is equal to inverse image length. Or, put a little bit more succinctly, 1 over d object plus 1 over d image is equal to 1 over the focus. So we have a new spherical wave. Okay, we have a new spherical wave, and the origin of the new spherical wave is 1 over d image, and the relation between the image, the new spherical wave, all right, and the original one that the lens had as an input is related through the focus, to the focus through this equation here, this thin lens equation. Okay, so this is something we're going to derive in a completely different way with Snell's law a bit differently, but we can see that just looking at it in terms of diffraction and wave fronts that impart this quadratic phase, we can get this equation which tells us that if I have in general a spherical wave input into a lens, it gets mapped into another spherical wave, okay, given by this thin lens equation. So we have 3 key points here for what a lens actually does. On one hand, it takes in a plane wave and gives you a spherical wave. All right, that's focusing. It takes a spherical wave and gives you a plane wave. That's collimation. And in general, if you have a spherical wave that's not right at that distance f away from the lens, it's going to map to another spherical wave. It's called a property called imaging. All right, and this is key. This is what imaging really is. We haven't studied it yet, but we're going to. And imaging is the mapping of points to points, and that's what an optical system such as a lens does. And this is crucial for understanding how images are formed. In fact, in your eyes, you have lenses right where your pupils are, and you have a screen roughly a distance f away called your retina. And if you're looking at something, you're looking at this computer screen right now, or your phone, or however you're watching this, and it consists of a bunch of small points. And each one of those point sources are being mapped through the lens in your eye to a point on your retina. And a point beside it is getting mapped to another point. And this is how images are formed. Okay, so this is what a lens actually does. But it does one more thing, which is very important in terms of this lecture. It actually is, as claimed in the beginning of the lecture, a Fourier transformer. It looks like a piece of glass, but it's actually an analog computer calculating the Fourier transform. Okay, and that's what you actually see on a lens when you are looking place a screen directly in its focus. Okay, so let's look at that. How is a lens a Fourier transform? And we've already done all the heavy lifting, okay? Look at this beast here, this Fresnel diffraction integral. What we're going to do is, remember we had our aperture, our E naught? And this is going to be our X prime, Y prime plane here, going along Z. And some point later, we're going to get a field which is described by this wave. So let's modify it a bit. Immediately after that x prime, y prime, z equals 0 plane, we're going to put a lens. Okay, we'll put a lens right here, a very poorly drawn lens, and look downstream, still a distance away. We're going to go to a distance f away. Okay, right. And what is that lens going to do? Well, it's going to impart a quadratic phase shift. So at that distance f away, this is the expression that we're going to get. And if we look very carefully, for that one particular distance, z is equal to f, that quadratic phase, that f in the quadratic phase is the same. It's a property of the lens. It's not going to change. But we can look at different planes. And if we're looking at the z equals f plane on this Fourier Fresnel diffraction integral, and these quadratic phases are going to completely cancel out. And that's how we got to the Fourier transform. Before we had to go all the way into the far field. Now we just need to put in a lens, and in the plane that we're interested in, we'll put in our lens and move a distance f away, and in that focal plane, in that z equals f plane, we get the exact Fourier transform without having to worry about the Fourier plane. So maybe it has a 25 millimeter or a 50 millimeter focus. That's exactly where we go to get the Fourier transform. So a lens is actually Fourier transforming our z equals 0 plane here. So if I put in, if I'm interested in taking the Fourier transform of an image, all I have to do is stick a lens here, look a distance f away, and I get the Fourier transform. There's going to be some talks about this later in the week by Matea and Janae, I believe, about the Fourier optics. So this is great, and we're almost done, but I want to put one kind of key point in here is, what about the objects? Remember the Fourier transform? The Fourier transform is in k-space, right? Now there is a small subtlety here, is that we're pulling out a result from the future that we haven't derived yet, but in a lens, the focal length, things coming into a lens at different angles, are going to generally focus to a plane. We call it the focal plane, right? So it's just going to be shifted up and down, all right? And at that focal plane, we're going to have a theta mapping to roughly delta x over f, okay? So plugging this in, we just have these relations between kx and similarly between ky. And that means we're going to get a physical space, delta x, of lambda f over 2 pi times kx. So we can imagine taking the Fourier transform numerically. It's going to give us some function of kx. I just multiply that by lambda f over 2 pi, and that's how much delta x I can physically expect. All right? And this is it for lenses, and the lens is a Fourier transform. So just to summarize it, wrap it all up, we asked what a lens actually does. And in terms of diffraction and Fourier optics, and in the wave way that we're looking at things, what a lens actually does is map a quadratic phase onto a beam. It's a phase imprinter. So there's 0 extra phase it right along the axis, that optical axis, z-axis, and the higher you get up, the more phase you get quadratically, okay? So it gives you this quadratic phase imprint. It maps plane waves onto spherical waves with this so-called focal length, which is just the radius of curvature divided by n minus 1. So if n is equal to 1, the focal length is infinity. That kind of makes sense, right? If you go from air to air, it doesn't do any focusing, right? So an infinite focal length here just means a plane wave. Okay, so this is a way we can think about it in terms of what it does to different waves. So it maps different waves. It maps plane waves to spherical waves. So a plane wave comes in, it gets converted into a spherical wave. That's what this quadratic phase does. A spherical wave, a distance f away, all right? Conversely, a spherical wave that's a distance f in front of the lens will get mapped to a plane wave. In other words, it'll get mapped to a spherical wave infinitely far away, right? So finally, we can just put a spherical wave anywhere and it maps points to points. These three phenomena are called focusing, collimation, and imaging, respectively. And this quadratic phase was very useful in terms of our Fourier optics picture because it gives us a shortcut to the far field. It actually warps us into the infinitely far away plane. So our angles get mapped to physical displacements, but at a finite distance away, okay? So the lens gives us the Fourier transform of the aperture. It's a shortcut to the far field. And that's it for lenses. That's it for this part of Fourier optics. And we're going to wrap it up this week by talking about a few hot topics in Fourier optics. We're going to talk about the convolution theorem and how to deal with repetitive structures, and we'll talk about analog filtering of images via Fourier optics. And we will see you then.